come up for the very first problem. I'm going to go ahead and zoom into it too so it's easier to see. But for the very first problem, you're going to go ahead and split it up into two different kinds of problems that you're going to work on, where you're distributing this entire term to each of these terms. Okay, this is one term, this is a second term. Okay, so I'm going to rewrite it so that I show that distribution. So I'm really doing -2 square root of 5x to the fourth, and I'm multiplying it by 3 square root of 20x to the third. And then for this one, I'm doing -2 square root of 5x to the fourth times -2 square root of 27x to the sixth. Okay, so here is my split up. I'm going to solve each of them individually. Remember on Friday, we said, okay, we're going to go ahead and do our coefficients first. So I'm going to do -2 times a +3. Then I'm going to do a radical house for my numerical radicals, which is 5 and 20. And then I'm going to do a radical house for just my variable radicals. So x to the fourth times x to the third. Okay, what is -2 times 3? -6. What is 5 times 20? 100. Is 100 perfect? Yes. So since 100 is perfect, I'm going to go ahead and put it automatically in the pink so that I know for me that I've got a perfect square here. What about x to the fourth times x to the third? What is that going to equal? X to the seventh. Is that perfect? No, because it's an odd exponent. So I'm going to leave it in green. I've got x to the seventh. Okay, so before I start simplifying, I'm going to see, can I split x to the seventh up? Yes or no? Yes. I can split it up into a perfect square in pink and a non-perfect square, which would just be a single value of x, a single square root value of x. So if I take a single value of x out, what am I left with? It's going to be x to what power? The sixth. It's going to be x to the sixth power that is left over. Okay, we still have that square root of 100, and we still have that coefficient that's in front, that -6. So now we can start simplifying. Once I simplify the square root is gone. That radical is now gone. So I'm going to be left with -6 times 10 times x to the third. Because remember, when we take a radical, we take the root of an even power, we just divide the power by 2. Okay, that square root of x is still going to be left. Okay, then I'm going to go ahead and multiply all those blues together. What's -6 times 10? -60, and then times x to the third gives me just x to the third. So we get -60 x to the third square root of x. Okay, that's just this portion here. I still need to now work with this one. So same concept, we're going to multiply just the coefficients first. So I'm going to do -2 times -2. Then I'm going to multiply my radical values, my numerical values, 5 times 27. And then my radical for just my variables, x to the fourth times x to the sixth. Okay, -2 times -2 is +2, or +4, sorry, not 2. +4. So I'm going to go ahead and put a plus sign in front of it because I know now that since I got a positive, I'm going to bring that plus sign all the way down to my answer. Because I got a positive, I need to bring that plus sign down to my answer. Okay, and that gets me a 4. 5 times 27, 135. Is that perfect or non-perfect? Not perfect, right? 135 is not a perfect square. What about x to the fourth times x to the sixth? X to the 10th, perfect or not perfect? Perfect, so we're going to go ahead and put it in pink. I'm going to get x to the 10th. Okay, 135, let's go ahead and break 135 up. What perfect square does go into 135? 9. Thank you. Okay, square root of 9, and then we would be left with 9 times what? 9 times 15. Good. So we get 9 times 15. 9 times 15 gives us 135. So 9 is a perfect square. 15 is not. We still have that 4 in front of it. And we still have that square root of 10 that was perfect as well. Okay, so now I'm going to go ahead and take my perfect squares. So I have 4 times 3 times, I'm going to go ahead and bring that perfect square over here. Square root of x to the 10th becomes x to the 5th. And then that square root of 15 just comes down as square root of 15. Okay, and 4 times 3 times x to the 5th gives me 12 x to the 5th, and then square root of 15. I cannot combine these. Even though I do have radicals for both, they are not like radicals. They are not like radicals, therefore I could not combine them. This is my final answer. Okay, let's take a look at problem number 2. Problem number 2, it's just one simple one, similar to what we were doing for each of these. Multiply our numerical terms, or sorry, our coefficients first. We're going to do 8 times negative 3. Multiply just our numerical radicals, so square root of 12 times 6. And then multiply just our variable radicals. So we have x to the 5th times x to the 8th. Okay, 8 times negative 3 is going to give us negative 24. 12 times 6 is going to give us 72, so we have square root of 72. And then x to the 5th times x to the 8th is going to give us x to the 13th. We're just going to add those exponents together. 72. 72 can be broken down. What perfect square goes into 72, guys? 36. So we get 36 and 2. X to the 13th can be broken down. We're going to get x to the 12th, good, and x. Okay, we still have that 24 right in the front. Okay, now we're going to go ahead and take the square root of all those perfect squares. Square root of 36 is going to give me 6. And then the square root of x to the 12th is going to give me x to the 6th. Then I'm just going to bring down square root of 2 and square root of x. Now I just need to do 24 times 6. So negative 24 times 6 is going to give me a negative 144 x to the 6th. And then one radical. We're just going to put both of these under the same house, square root of 2x. And that's our final answer. Any questions? Okay, so what we're going to be doing today is we're going to finish up with learning how to divide with rationals, with radicals, and do what's called rationalizing the denominator. Okay, so go ahead and turn to the next page. Okay, we're going to title it Quotients with Radicals. And rationalizing denominators. Okay, so quotients, that's just a division problem. When you're looking at a division problem, if the entire thing is under a radical, it basically looks like a fraction, 5/9. So we have the square root of the fraction 5/9. We already know how to do something like this because at the very beginning of the unit. We talked about if you have a fraction, which is basically a division problem, under a radical, it basically means that what you're doing is the square root of the numerator and the square root of the denominator. So the first thing that you always want to check before you ever start working with a problem like this, you first want to see, is the denominator a perfect square? So we're going to write that down. You're first going to check if the denominator is a perfect square. So in this case, is the denominator a perfect square? Yes or no? Yes. Square root of 9 in this case is a perfect square. So I'm going to go ahead and highlight it in my pink. Okay, I'll put a little star by it. This is perfect, which means I can go ahead and take the square root of 9. So I'm left with the square root of 5 over, what's the square root of 9? 3. The next thing I do is see if I can simplify any further, meaning my numerator. Can I simplify my numerator? No. Okay, so that would be the second thing to do, though. The second thing, simplify as much as you can. Okay, if you can simplify, you simplify. If you can't simplify, then that's your final answer. Square root of 5 over 3. Okay, let's take a look at another problem. Got the square root of 12 over the square root of 27. All right, so first thing that I'm going to check, is my denominator a perfect square? Is that a perfect square? Is 27 perfect? No. So what I want to do is I want to try and see if I can simplify. So by simplifying, first I'm going to see, as just a fraction, 12 over 27, can I simplify 12 over 27? Yeah. What are they both divisible by? Not 2, 3, right? They're both divisible by 3. So I'm going to simplify the fraction. Not simplify as in simplify radicals. I'm going to simplify the fraction first. They're both divisible by 3. By doing that, I'm now going to get the square root of 4 over 9. Is the square root of 9 a perfect square? Yeah, right? Square root of 9 is a perfect square. So if I go ahead and just break that apart, that's square root of 9. What about square root of 4? Is that a perfect square? Yeah, square root of 4 is a perfect square. So I'm going to put them both in pink. When I simplify it, what's the square root of 4? 2. What's the square root of 9? 3. And that's it. 2/3 would be my answer. But like I said, before you ever simplify, so normally in a problem, we always go simplify first, then work with the problem. When it comes to fractions with radicals, you want to see if your denominator is perfect first. Because there might come a time when you have a perfect square for the denominator, but you could also simplify. You don't want to simplify yet. So like, for example, I have the square root of 80 over 25. 80 over 25 can be simplified, can't it? They're both divisible by what? 5. They're both divisible by 5. However, I don't want to simplify because 25 is perfect. I want to deal with a perfect square first. I want to deal with that perfect square first because it makes it easier. Because you're not allowed to be left with a radical in your denominator. That is the number one rule for fractions. You are not allowed to leave a fraction with a radical in the denominator. It will then be considered wrong. So if I were to have divided both by 5, I'd be left with square root of 5 at the bottom. So then I'd have to go through and do what's called rationalizing, which is just an extra step if I already know I've got a square root that's perfect here. This is a perfect square. I'm going to go ahead and simplify that first. So I have square root of 25, and on the top I've got square root of 80, which is not perfect. Okay, so when I do that, square root of 25 gives me 5 for my denominator, and then I've got square root of 80 for my numerator. So all I need to do now is simplify square root of 80. Let's break 80 up. What perfect square can go into 80? 4 can go into it, yeah. So you'd have 4 times 20, but 20 can also be broken down. So there's a larger perfect square that can go into 80. 16, very good. So you have square root of 16 and square root of 5. All of it over just plain 5. Notice I'm doing these different colors, right? Remember before I said, hey, pink means it's perfect, green means it's not perfect, and blue meant it's not a radical at all. It's just a number, not a root. Keep that in mind, because at the end, I don't want you guys going, oh, square root of 5 over 5, I can divide them both by 5. You can't, because one of them's a radical and one of them's not. So be very careful about that, okay? If I take the square root of 16, what do I get? 4. Because I'm taking the square root, am I going to leave it pink anymore? No, because I'm telling myself it's done. I took the radical. I no longer have that root there. It's a 4. Square root of 5 is going to be just the square root of 5. And this is all over 5. So now, notice I've got 2 blues, don't I? I have a 4 and a 5 in blue. That I could try and see, hey, 4/5. Can I simplify 4/5? Can you simplify 4 over 5? No. Those I could try and simplify if possible, because they're of like color in this sense, meaning that they are of like value, like characteristic. They're both coefficients or numbers not inside radicals. Okay, but we can't simplify any further. This is it. That's as far as we can go. Okay, what is the first thing we always want to check? David? If the denominator is a perfect square. Is the denominator a perfect square, guys? No, 98 is not a perfect square. So since it's not a perfect square, what's the second thing that we want to try and do then? Simplify it. Can we simplify 40 over 98? Do they both have a value that they're divisible by? What are they both divisible by? 2. They're both divisible by 2. Yeah, because they're both even. They're both divisible by 2 because they're both even. So that gives me the square root of 20 over the square root of 49. Do I have a denominator that is a perfect square now? Yes. My denominator is a perfect square, so I'm going to go ahead and highlight that in pink. Okay, what about square root of 20? Is square root of 20 perfect? No. Can I make it have a perfect square? What perfect square can go into 20? 4. So I'm going to have square root of 4 times the square root of 5, because 4 times 5. And then all of it over square root of 49. which was perfect. Okay, so let's go ahead and take our perfect squares now. What's the square root of 4? 2. So I get 2 square root of 5. And then what's the square root of 49? 7 over 7. Can I simplify 2 over 7? No. So then this is my final answer. It's a lot of steps to it. And right now we're dealing with the easy stuff. Sarah, your face is classic. She's just like wide-eyed, like, are you kidding me? This is the easy stuff. This is the easy stuff. Okay? Try one on your own. Oh, wait, no, I don't want to do 75. Yeah, yeah, I do want to do 75. Okay. Try that one on your own. Okay, let's go ahead and go over this. So for problem number 5, square root of 24 over 75. Is 75 a perfect square? No. So if 75 is not a perfect square, the first thing we're going to try to do is see, can we simplify 24 over 75? 24 over 75, what are they both divisible by? 3. They both can be divided by 3. So when I break this up, I'm going to get the square root of 8. Is square root of 8 perfect? No. So I'm going to go ahead and just write square root of 8. And then 75 divided by 3 gives me 25. Is 25 perfect? Yes. 25 is perfect, so I'm going to go ahead and put that in pink so I get square root of 25. Okay. Now, square root of 8. Can I break 8 up? Yeah. 8 can be broken up into a perfect and non-perfect square. What perfect square goes into 8? 4. So we get square root of 4 times the square root of 2. Good. And then all of that is over the square root of 25. So now we're going to go ahead and take those perfect squares. What's the square root of 4? 2. What's the square? And then we've got the square root of 2 here. And then what is the square root of 25? 5. And then 2 over 5. Can we simplify 2 over 5? No. So this is as far as it's going to go. Okay. Let's try another one. One more on your own. Square root of 80 over 36. Square root of 80 over 36. Go ahead and try that one on your own. All right, let's go over this one. All right, square root of 80 over 36. Is 36 perfect? Yes, square root of 36 is perfect. So I'm going to go ahead and put square root of 36 on the bottom in pink. What about square root of 80? No, square root of 80 is not perfect. So I'm going to go ahead and break it up. What is a perfect square that can go into 80? 16. So we get 16 and, oops, I just did that in the wrong color. Square root of 16 in pink, and then square root of 5. Okay, so we've got square root of 16, square root of 5 over the square root of 36. Let's go ahead and break that down. What's square root of 16? 4. So we get 4 square root of 5. And then what is the square root of 36? 6. Okay, so now the 4 and the 6 are outside of a radical. So can we simplify 4, 6? Yes. These are both divisible by what? 2. I can divide this by 2. I can divide this by 2. That radical, that square root of 5, remains unchanged. It's going to remain unchanged. 4 divided by 2 is going to give me 2. So I get 2 square root of 5. And then 6 divided by 2 gives me a 3. So I get 2 square root of 5 over 3 as my final answer. You've got to make sure that you can simplify everything that's outside of the radical as far as you can, if possible. Okay, that's just numbers. Now we got to add variables. And then we got to add rationalizing denominators. So let's go into some variables. Let's add some variables in. Let's switch to the next page. It'll be fine. I promise. All right, that was problems. All right, number 7. Okay, so let's add a few variables in. It's the same concept, same process that you would follow, but just now with some variables and exponents involved in it as well. So we have x to the 5th over 81x. Okay, first thing that we want to do is check, is the denominator a perfect square? Is the denominator a perfect square? Is the entire denominator a perfect square? No. When I say, is the denominator perfect, if only part of it is, and the part of it's not, then the answer is no, it's not a perfect square. 81 is perfect, but x is not perfect. X is not perfect. However, if I just had x to the 5th over x, do we know how to work that problem out? Yeah, I see you guys shaking your heads, yes. Yes, we know how to solve that. X to the 5th over x, this is just an exponent problem. When we are dividing by the same base, what do we do with exponents? Say it louder. Subtract. You subtract your exponents. If it was just x to the 5th over x, we know we would subtract those exponents. So if I need to show that to you guys again, I'm going to do this in orange. This little portion right here, if I write that out, that is x times x times x times x times x over x. That means I can take one of these and cross those off with the top, leaving me with just 4 x's on the top. So that my problem now becomes the square root of x to the 4th over just 81. Now am I dealing with perfect square entirely on the bottom? Yeah. And in fact, I'm also dealing with a perfect square on the top. X to the 4th is a perfect square because the square root, or the exponent, is even. And then square root of 81 is a perfect square. What's the square root of x to the 4th? X to the 2nd. And then square root of 81 is 9. So there's my answer. Okay, let's go with 20b to the 7th over 25b to the 3rd. 20b to the 7th over 25b to the 3rd. So again, looking at my denominator, 25 is perfect, but b to the 3rd is not. So the first thing I want to do is try and simplify those b's. If I simplify those b's, what am I going to be left with? B to the 4th. And where will b to the 4th belong? At the top. So if I simplify it, I'm just going to subtract the exponents. Okay, I'm going to subtract the exponents. So that's going to leave me with a new problem of the square root of 20, which is not perfect. And then square root of b to the 4th, which is perfect, on the top. And then on the bottom, I'm going to be left with square root of 25, which is perfect. Okay, now square root of 20, though, I can break square root of 20 up. Let's break square root of 20 up. What perfect square can go into 20? 4. So square root of 4, and then square root of 5, and then still square root of b to the 4th. All of it over square root of 25. Okay, so now it's time to simplify. Square root of 4 is 2. Square root of b to the 4th is b to the 2nd. And then we have square root of 5. All of this over square root of 25 is 5. And I cannot simplify anything from top to bottom. So there's my final answer. Try one on your own, and then we're going to move on to probably the most difficult part, which is the rationalizing the denominator. Don't make that sound. It'll be fine. All right, we have 65 x to the 5th over 125 x to the 15th. Try that one on your own. Square root of 65x to the 5th over 125x to the 15th. All right, let's take a look at this one. So we have a non-perfect square on the bottom, 125, and x to the 15th. Those are both not perfect squares. Let's go ahead and simplify the variables first. So x to the 5th over x to the 15th. If we subtract those exponents, what are we going to get? X to the 10th. And is that going to go on the top or the bottom? On the bottom. Because of the fact that it's more heavy, right? We have more x value on the bottom. If you subtract those without worrying about order, you just subtract 15 and 5, you'd be left with 10, and it would be 10 of them remaining on the bottom. All of the ones on the top would be disappearing. You'd left with 10 x's on the bottom, so x to the 10th would remain on the bottom. So what I'm going to go ahead and do is I'm going to split this up into two different problems. I'm going to focus on just the numbers and then the variables. So I know I had x to the 5th over that x to the 15th. So let's focus first here. So the numbers 65 and 125, they're both divisible by what? 5. Because 125 is not perfect, I'm going to go ahead and try to simplify them. They're both divisible by 5, and that's going to give me 13 over 25. 13 over 25. Is 13 perfect? No, so I'm going to get square root of 13. Is 25 perfect? Yes, I'm going to get square root of 25. Okay, and then when we already know that we subtracted the exponents here, so we were left with nothing on the top. So if we have nothing on the top, what do we put? A 1. And is 1 perfect? Is 1 perfect? Yes, that is the very first perfect square that we learned about. Because the square root of 1 is just 1. 1 times 1 is 1. Okay, and then on the bottom, we're left with x to the 10th power. Is x to the 10th power perfect? Yes. X to the 10th is perfect because the exponent is even. Okay, so now we just go ahead and take our square roots of our perfect squares. So we're left with square root of 13 on the top times 1. Square root of 13 times 1 is just square root of 13. And then on the bottom, square root of 25 is 5. And square root of 10, or sorry, square root of x to the 10th power is x to the 5th power. Okay, all right. Rationalizing the denominator. Let's get into that. We'll start easy. If I give you something like square root of 5 over 12. Square root of 5 over 12. 12 is not perfect. We can all agree on that. And I think we can all agree that you cannot simplify 5 and 12. You cannot simplify 5 and 12. So in a situation like this, you have to do what's called rationalizing your denominator. Rationalizing the denominator means that you're just going to multiply both the top and the bottom by your denominator. That's it. You're just going to multiply the top and the bottom value by your denominator. So if I break these apart, I'm going to break these both up into their non-perfect squares, the square root of 5 and the square root of 12. And I'm going to multiply both the top and the bottom by the square root of 12. I'm going to multiply both the top and the bottom by the square root of 12. By doing so, 5 times 12 now gives me the square root of 60, but 12 times 12 now gives me the perfect square of 144. Okay, so before I start taking any square roots, can I simplify 60? Can I break 60 up into a perfect square and a non-perfect square? What perfect square can go into 60? 4. Square root of 4, and then the square root of 15. 15 is not perfect. All of this over the square root of 144. Now I can start taking my square roots. What's the square root of 4? 2. So 2 square root of 15. All of it over, what's the square root of 144? 12. Okay, so I have 2 square root of 15 over 12. Can I simplify anything? 2 over 12? Can that simplify? They're both divisible by what? 2. So I'm going to divide the 2 by 2. I'm going to divide the 12 by 2. And 2 divided by 2 is just 1. So I have 1 square root of 15, or just square root of 15. 12 divided by 2 is going to give me 6. So I get square root of 15 over 6. And that's my final answer. So rationalizing the denominator is the very last thing that you attempt to do if you cannot simplify your denominator into something that is perfect. That is the last attempt that you make. Is if you cannot simplify your denominator into something that is a perfect square, then you have to resort to rationalizing the denominator. Look at another one. Square root of 7 over 2. 2 is not a perfect square. I also cannot simplify 7 over 2. So that means I have to rationalize the denominator. So if I break this up into square root of 7 over square root of 2, to rationalize the denominator, I'm going to multiply the top and the bottom by what value? Square root of 2. Whatever my denominator was, I'm going to multiply by it so that way I can get rid of the radical. Okay? 7 times 2 is going to give me 14, which is not perfect, so I'm going to put it in green. Square root of 2 times square root of 2 is going to give me square root of 4, which is perfect, so I'm going to put it in pink. 14 cannot be broken down because the only factors of 14 are 1, 14, 2, and 7. None of those are perfect except for the 1. So we cannot break it down any further. It's going to remain square root of 14. Square root of 4 becomes 2. And then that's it. I'm done. I've simplified it as far as I can. Try this one on your own. Try that one on your own. All right, let's take a look at this one. So a 2 square root of 80 over square root of 7. Again, 7 is not a perfect square, nor can I simplify 80 over 7 any further. So that means square root of 7 is as simplified as that would get. So we have to rationalize that denominator. That means we're going to multiply both the numerator and the denominator by square root of 7. Now that 7 gets multiplied to the 80, not to the 2. Because the fact that it's under a root, It can only be multiplied with another value that is under a root. It does not get multiplied with that 2. So that 2 is going to stay exactly as it is. It's going to remain on the outside. So I'm going to go ahead and put it in blue. Square root of 80 times the square root of 7 becomes the square root of 560, which is not perfect. So I'm going to put it in green. Square root of 7 times square root of 7 becomes the square root of 49, which is perfect. That's the whole idea of doing that. We're trying to make a perfect square. I'm going to put it in pink. All right, 560. 560 can be broken up into a perfect square and a non-perfect square. Who figured out what the perfect square was that can go into it? Anybody? No? Okay. 16. 16 can go into 560. It can go into it 35 times. So you get 16 and you get 35. Square root of 16, square root of 35. Okay, and all of that is still over square root of 49. All right, so now we just go ahead and start simplifying. We still have that 2 times, what's the square root of 16? 4. And then square root of 35. Over, what's the square root of 49? 7. Now we can still multiply 2 times 4. 2 times 4 is going to give us 8. So we're going to get 8 square root of 35 over 7. And that's as far as we can go. We cannot simplify any further because 8 and 7 cannot be simplified. Please do not make the mistake. I have kids every year who go, oh, but 7 can go into 35. Why can I not simplify 7 and 35? Why can I not simplify 7 in that 35? Somebody raise your hand, tell me why. Con? Aaliyah? Because 35 is a radical and 7 is not. 35 is a radical, 7 is not. Therefore, you cannot simplify them. You can only simplify radicals by other radicals. So be mindful of that, okay? All right. Last step of difficulty. The highest level, I promise. It won't get any harder than this part. We're going to add variables. All right, so square root of 13 over the square root of 50x. Square root of 15 over the square root of 50x. 50 is not perfect. X is not perfect. We cannot simplify 13 and 50. Okay, they are not divisible by anything in common. So that means, again, we're going to have to go ahead and rationalize the denominator. But this time when we're rationalizing, we have to rationalize not only the number, but also the variable. So that means I'm not just multiplying by square root of 50 on top and bottom. I have to multiply by square root of 50x on the top and the bottom. And I want to know, do you guys notice a pattern here? Every time I rationalize the denominator, okay, I had a square root of 12. So I multiplied by square root of 12, and all of a sudden what happened when I simplified my my denominator became a what? What? A 12. Okay, once I finished rationalizing and then I took the square root, it just became 12, no longer a radical. Same thing here. Hey, I have to rationalize that square root of 2, so I multiplied by square root of 2, which gave me square root of 4, but then I'm left with just 2, no longer a radical. So square root of 2 became just 2 when I finished rationalizing. Square root of 7 became just 7 when I finished rationalizing. So do I really need to go through and go, okay, 50x times 50x, and then I'm going to get, 2500x squared, but that's going to simplify to 50x again. Do I need to go through all of that? Or can I just go, when I rationalize those two, I'm going to be left with 50x, but no longer have a radical. I can do that. Make it simpler for you. Because you already know that that's the goal in mind, is to get rid of that radical. A radical times itself is just the radicand, no longer a radical. It's just whatever was inside, okay? So I'm going to skip all the nonsense and just put my answer on the bottom as 50x. No radical anymore. Now I can't skip the nonsense for the top though. I have to actually go through and multiply those. So 50x and 13. When I multiply 50 times 13, I'm going to get 650x. But I can go ahead and break 650x up. I'm going to have a perfect square that can go into 650, which is 25. And 25 can go into it 26 times. So I have 26x as my non-perfect square. I'll zoom in a little bit more so you can see it easier. So square root of 25 and square root of 26x will give me that 650. And all of this is over 50x. What's the square root of 25? 5. So I have 5 square root of 26x. All of it over 50x. Now let me just look at the blue. Can I simplify the blue? Can 50 over, or 5 over 50 be simplified? Yeah, they're both divisible by 5. They're both divisible by 5, so that my final answer here is just going to be, well, 5 divided by 5 is 1, so I'm just left with that square root of 26x over, what's 50x divided by 5? What's 50 divided by 5? 10. So I'm left with just 10x. I cannot simplify any further. That's as simplified as it's going to get. Okay? All right, you have a homework. Which we'll get to after this drill.